with reminding you what axions are, what the gravity conjecture is, and how Euclidean wormholes may be qualifying as the so-called weak gravity conjecture objects. I will explain what that means. And then I will come to a more complicated and confused story, summing over all these wormholes. So Coleman's wormholes proposal, which has problems and these problems have recently re-emerged and be discussed in the context of black hole entropy, ADS, CFT, global symmetries, and so on. And finally, on a slightly different subject, I will discuss the need for topology change and eternal inflation, which somehow also, in my mind at least, fits into the general story of non-trivial topologies in 4D quantum gravity. All right, so let us start here with just a very basic set of statements. So axions. So one of our key players will be axions or axion-like scalars. And as you know, these are just scalar fields which are periodic. I'm giving here a canonical kinetic term, and I couple them to FF dual of a non-abelian gauge theory with this coupling phi over f, f being the decay constant. And in this case, of course, since the gauge theory has fluctuations, in particular, it has instanton fluctuations, and you can think of those as lumps of action distributed in spacetime, driven here. And so these lumps of action happen to couple via this term to the axions, and if you sum over all such lumps, you create an effective potential, cosine phi over f, and then the complete shift symmetry of this axionic scalar is broken to the periodicity, to phi equals phi 2 pi f. And this remaining shift symmetry, of course, cannot be broken anymore because it is gauged. Good. So the next main player will be the gravity conjecture. So everybody knows the slogan, gravity is always the weakest force. And more concretely, the statement is that for any U1 gauge theory, there exists a charged particle with mass smaller than charge. And by charge, I will here mean the product of gauge coupling and some integer charge. And the Planck mass will be set to unity almost always. You will see when I deviate from that. And so now, of course, to apply this to axions, one needs to generalize. This directly does not apply to axions, but the generalization is extremely straightforward. So the first step is that one recalls what the action of a standard one-form gauge theory is. So there's a two-form field strength squared. Then there is the action for the charged particle. So the main part is just the mass times the world line integral, and then there's a coupling the coupling to the gauge potential A1, one form integrated along the one-dimensional world line. Now that is obvious how to generalize to strings, domain world, and so on. You simply consider now a gauge theory, not as a one form, but as a P form gauge potential. Then you have a P plus one form field strength. The integral over the world line turns into an integral, which I give here, over the world volume. I still call the prefactor mass. It's now actually a tension. And of course, in addition, there's a term with a P form gauge potential integrated over the P-dimensional world volume. So that is obvious. What is less obvious, but also true, is that you can generalize to lower dimensional objects. In this case, instantons, and with the gauge field being now the axion. Here's the action. So this is now the one form field strength squared. And the gauge potential is now not called A0, but it's our axion phi. For the action of the instanton, I write simply still m at the moment, but it's just now a number. I mean, there is no integral to be made because it's a point. And then there's also the term where you kind of integrate the zero form potential over the world volume, but that's of course just evaluating the scalar at the location of the instanton. And that compares very nicely to my previous phenomenological instanton action, where you have d phi squared, trace f squared, and 1 over f phi trace ff dual. So this calculates the action of the instanton, and this calculates the coupling. So here it's written again. The trace of the f squared integrated is the instanton action, and it is what was before called m the kind of fundamental action of a point-like in space-time particle or object, instanton. So here, once again, the picture. So standard gauge theory, gauge potential, particle going through it, instanton situation, axion, background, instantons as points in space-time, and the action is evaluating the axion field at the points of the instantons. Okay, so now let's bring these two things together. So brings this together with the gravity conjecture. So recall that the instanton induced potential actually is not that just the cosine I gave you before, but has a prefactor, e to the minus s instanton. It just suppresses this tunneling process exponentially. And now, as you have seen on the previous slide, the coupling, which I called Q in the gauge theory case, is now 1 over f. So let me go back. You see here this 1 over f in the coupling term, which is a typical situation for more or less a definition of how the coupling of an axion is defined. And the m turns into s instanton. And now, so the condition that the mass is smaller than the charge now turns into the statement that the instanton action is smaller than 1 over f, 1 over the decay constant of the axion. And so I'm now telling you something very well known, has been discussed very intensely last few years, that theoretical control, i.e. dilute instanton gas approximation, of course requires s instanton being larger than unity, and that by the Buff equation implies that f axion always is smaller than 1, and hence, which is a slogan, large field natural inflation is in trouble from the weak gravity conjecture. And that will not be my main subject today. I will focus more on a possibly more interesting situation, which we all know, is existent at least in many particle physics models, axions with f smaller than 1. Sub-Planckian axion decay constants. And in this case, the gravity conjecture is also not empty, but it actually represents then a bound on the strength of instanton effects. Yeah, this condition that S instanton is smaller than 1 over F now becomes the statement that X of minus S instanton is bigger than X to the minus 1 over F. So we have an explicit bound on how strong your potential always at least has to be, minimally has to be. So how is that related to wormholes? Let's now give another step, or go another step, and relate this to wormholes. And the basic idea, as you see here on top, is that wormholes are, if you wish, the analog of the charged black holes, which of course always satisfies the gravity conjecture, at least for sufficiently high charge. And so the claim is that the wormholes play the same role in the case of the axion, and are important, hence an important ingredient in the quantum gravity side of this weak gravity conjecture. So, well-known old statement in Euclidean gravity, with an axion phi, there exist always instantonic solutions. They are called Wittig-Schrödinger wormholes, and they are very simple. So the picture I'm drawing here is obviously, two-dimensional Euclidean space, but you should think of four-dimensional Euclidean space. So here's the space, and then you can draw such a wormhole, and I leave here open where it ends. It could end in some different universe, or it could end on the same space-time. Of course, the ends have to be far away, far enough separated, such that they don't interfere with each other. And this throat that we form here is supported by the gradient energy of the axion. So if you have an axion, the solution exists, and the axion flows through the throat. And this is claimed that, the story has kind of restarted. The old story has been restarted with this paper because they argued that the shift symmetry of the axion field is broken unavoidably in gravity by those effects. All right, so let me spend maybe 2 slides, because maybe it's not familiar to everybody, how to derive this and how to understand the simple parametrics of the solution. It's actually much simpler to understand it not on the axion side, but on the dual two-form gauge theory side. So for that, let me rewrite the action. So the action is Einstein-Hilbert here, plus f squared d phi squared, where now I have rescaled the axion such that it is 2 pi periodic. And hence the f squared is in front of the kinetic term, of gradient term here. Now that's a one-form field strength squared, so you can dualize it in the standard way how we dualize gauge series by a Hodge star and multiplying by the coupling F squared. And the dual side potential is then a two-form such that this is a three-form, so H3 is roughly speaking star of F1 in 4 dimensions. So now my action is this. It's exactly the same theory. The coupling has switched and now this is 3-form squared. And the throat now exists due to a compensation of these 2 terms and it's easy to derive. So I now, for the moment, reinstate and plant because it will be simpler to see how things work. I allow for n units of flux, flux of the 3-form H3 equal dB2 on the transverse 3-sphere of the throat. Yeah, I remind you that here, of course, in this picture, I cut the throat and I get an S1 because I'm 2 dimensions. If I cut such a throat in our real world, the cut will be a 3-sphere. So the solution described above exists because the 3-sphere carries, let's say, n units of H3 flux. Quantized, so cannot go away, cannot decay. And I call the typical radius of the throat R. Don't confuse this with the calligraphic R for the Ricci scalar. So now, as a simple equation, the Einstein-Hilbert term gives me a Planck squared radius to the -2, just on dimensional grounds. And the flux side is n squared for the flux number over f squared for the prefactor and r to the -6 because the H3 is a 3-form flux scales like 1 over r cubed, a square, r to the -6. And then you would set these 2 equal, you get a relation, and you can calculate everything. You can calculate the radius of the solution, the action, everything. This is now fiddling around with numbers. So a key number you should remember is this one. That is already the number given by Giddings and Schrödinger many years ago. So the action is now expressed through n and the instanton decay constant. And parametrically, this agrees with the gravity conjecture instanton action. And so a key point, which I mean, maybe almost trivial, but which we made, and I think is an important point, is that this relation may be taken to precisely define what we even mean by instanton gravity conjecture. You see, on the gravity conjecture, usually you fix the pi factors on everything, arguing on the basis of extremal black holes. They don't exist in this case, but the wormhole exists. And this fixes a number, and this number actually turns out to be important in phenomenological applications, if you believe them, of this kind of instanton sum. So let's go on. The wormhole curvature scale is square root f over n, always with a Planck equals to 1. And now, of course, you don't trust all wormhole solutions. You trust only those ones which are large enough, so their local curvature is smaller. The local curvature scale is smaller than the cutoff of your theory. And that translates into this condition. So you trust only, at small f, you trust only wormholes which are sufficiently large in n, highly charged. So this fixes the lowest number n that you can trust, and hence it fixes the minimal size of the instant correction to a potential. So the potential correction is e to the -s, that's standard. Then I told you e to the -s is the same as e to the -n over f, and this is e to the -1 over cutoff squared for the most relevant wormhole that you trust. So in fact, you can have very flat potentials in spite of wormhole effects if your cutoff is low enough in principle. And for gravitational instantons not to prevent inflation, the relative correction must be small. So delta b over v must be small. It's e to the -1 over cutoff squared over h squared, h being the Hubble scale during inflation. And it's clear that for a Planck scale cutoff, this is never possible. So for a Planck scale cutoff, you can't have axionic inflation. But if the UV cutoff is small, in principle can be as low as h, and h is much smaller than unity, as we know from data, then of course delta v over v is e to the -1 over h squared. And now if h is small parametrically, you see this becomes a small number, in fact, a very small number. So unfortunately or fortunately, wormholes a priori, even though the whole story beautifully fits together with the gravity conjecture, do not constrain flat potentials. However, wormhole effects can be interesting phenomenologically in many other ways. So let me give two examples. The story is, of course, again, an old one. Going back to Coleman, Lee, Ray, has been revisited and refined, well, also in recent years. So for example, let's talk about the Qcd axiom. If the decay constant is relatively high, then the following can happen. We have the usual cosine from Qcd, which is crucial to solving the strong CP problem, but then you have possibly with a different phase called delta, a wormhole contribution. And it turns out that if the cutoff is high and f is large enough, in fact, the solution to the strong CP problem is lost. So wormholes can be in the way of the axionic solution to the strong CP problem. Now, interesting positive observational consequences exist in the context of black hole superradiance and ultralight dark matter. For example, let me spend one slide on fuzzy dark matter, which is by definition a scalar that is so light that its de Broglie wavelength affects subgalactic scale structure. So the mass needs to be smaller than 10 to the minus 21 eV. So now if the wormhole is the universal and model independent effect of shift symmetry breaking for that scalar, then of course this fixes f in terms of m, or the other way around, by this relation. This is just a relation for the potential I had before. But at the same time, the abundance of fuzzy dark matter is determined by this well-known formula for axions. If they have a certain deviation from the minimum in cosmology, then they start oscillating, so this formula holds. And together, it turns out these relations lead, in fact, to an interesting slight clash. One finds that the mass should be slightly larger than 10 to the minus eV, just based on the wormhole-like potential. So, and this can be avoided with some model building in concrete stringy settings. Here, I refer you to this paper. So there's an interesting relation here between very fundamental quantum gravity statements about flat potentials and some phenomenological applications like Qcd Axiom and fuzzy dark matter. Now that was kind of the nice pheno part of the story. Now I come to the less nice part, namely, motivated by the above, we started to think a little bit about the old story of summing over all these wormholes. And there are deep conceptual issues. I mean, famously known due to Coleman's and Preskill's and other people's work at that time. Once one allows for wormholes, then the first observation is one must allow for baby universes, because if you have this wormhole, what I did so far, I treated each of its ends as an instanton. And the motivation was simply because from the perspective of the axion, I didn't maybe explain that well enough. From the perspective of the axion, this wormhole end and the instanton behave exactly the same way. Yeah, just because basically this cut carries 1 unit of the dual H3 flux, this makes it exactly an instanton. But now really it's a handle. And if you cut spacetime here, it means that you have created an intermediate state with a baby universe. I mean, a separate three sphere from our perspective. And then you can sum over all of those. You have to sum over all of those. That gives you something called alpha parameters. Let me explain in one slide. So a priori, this handle leads to a horrible non-local interaction, which I wrote down here. Expanding this gives you all possible handles added to your spacetime. But then, of course, you can resum it. You write it as an integral over some parameters alpha. You see that by Gaussian integration, this gives you back the left side integral. And then ideally, you sum over all alphas, and these are the alpha parameters of Coleman. And you can convince yourself that if you don't use the Euclidean picture, but rather the Hilbert space picture, evolution in real time, then these alpha parameters represent something that has been called the baby universe state. It's a state which characterizes, in addition to our spacetime, how many separate three spheres we have, and in which linear superpositions they are. So this renormalizes our constant of the prefactor of e to the minus s cosine phi over f. So actually, opposite to what I was advertising before, you don't really know how to calculate this term if it comes not from instantons, but from wormholes. What is much worse, the sum over these alpha parameters, in fact, renormalizes not only the axion potential, it renormalizes in principle all coefficients of your effective operators of your theory, and they appear to be not predictable in principle. Instead, most naively, 4D measurements collapse the space of all these alpha parameters to known constants, which promotes all constants of your field theory to basically unknown numbers to be measured. Now, what is worse in a global perspective, you need to sum both over 4D geometries and alpha parameters. And that summation leads to a catastrophe known as a Fischer-Susskind-Kaplanowski catastrophe, based on the fact that you get essential contributions even from very large wormholes. And another key problem of the story is that you clash with locality on the CFT side of ADS-CFT. Now, ADS-CFT is by now considered to be like almost a holy ingredient of our understanding of quantum gravity. But this story of summing over wormholes appears to lead to problems. Actually, most actively discussed in recent years in the context of SYK, where it really has been shown in a 2D toy model, if you wish, that on the CFT side, you don't get a single CFT exactly due to wormhole effects, but a sum over CFTs. So then, what is even worse, if you think of these alpha parameters, you realize immediately that it's not sufficient to sum over alpha parameters. You really need to give the alpha parameters, this baby universe background in which we live, some dynamics of its own. And to see this, consider the 1+1 dimension analog of string theory. So let's assume our real gravity is now 1+1 dimensional, and it's the worldsheet theory of a string. Then, of course, as is well known, the alpha parameters characterize the geometry of the target space. So if you think of a large string worldsheet, it can have handles, it can have coupled to background fields. This is all due to propagating closed string diagrams, which are precisely our wormholes of before. And in this case, we know what the background dynamics is, at least in some approximation. I mean, we don't really know it, it's string field theory, but we know that at some level of approximation, it is a 10-dimensional quantum field theory. We have no idea what the analog of this in 3+1 dimensions is. And so given this situation now, for many authors, it appeared very plausible and maybe advantageous to dismiss wormholes altogether, simply to get rid of them, to say that they are not there. But this is not easy, because we know that in string theory, wormholes correspond to string loops, and they are an essential part of the theory. And so forbidding topology change, which would be a way to get rid of them, appears not to be warranted, at least not for somebody who likes string theory. Maybe there's a good reason to forbid topology change in certain circumstances, for example, for D larger than 2. And moreover, arguments have been given, independently of this, arguments have been given that giving Strominger solution has negative modes and should hence be dismissed. I mean, most notably early on by Valery Rubakov, one of the first speaker of this conference this morning. So this has been analyzed by many following papers. Let me just only mention the most recent paper by Logis, Xu, and Sudir, which gives me the impression that the balance is turning here in favor of stability. So it appears not to be, they argue that choosing the right boundary conditions, you don't see the instability, and giving Strominger is a proper calculation. So let me now briefly comment on a few more recent developments. Recently, as of course all of you know, there has been a proposal for calculating the entropy for evaporating black holes using the so-called islands method. And there has been a Euclidean quantum gravity side of the calculation, which essentially relies on wormholes. So if one trusts this whole story, it seems that that wormholes have to have a role, have to be a key player, in fact, in our understanding of also 4D quantum gravity, because clearly the black hole evaporation problem should be solved also in 4D. And motivated by this, there has recently been devised a new 2D toy model developing this early Coleman calculation by Marolf and Maxfield. In essence, they were able to sum over more complicated topologies in just single handles. And they proposed that the baby universe Hilbert space, I mean, the space of all these separate spheres, has to be modded out by a certain equivalence, which roughly corresponds to the 1 to 2 baby universe transition. And this significantly reduces the size of the Hilbert space. And then there has been a conjecture by McNamara and Buffer that in 4D this becomes even stronger, although nobody knows how to do a calculation there. It should be even stronger, and the baby universe Hilbert space would be one-dimensional, in which case you could have both baby universes, but not the arbitrariness of other parameters. And the key question here, of course, is whether we will eventually be able to do a proper calculation for this in D equals or larger than 4, and whether and in which form averaging on the CFT side is part of the solution, as happens in SYK. Yeah, the idea here being that, as I said, in ADS CFT, you would have to claim that on the CFT side, some form of averaging, maybe averaging over many CFTs, maybe some averaging feature of a single CFT, as described in these papers, has to come in to actually be able to discover the effects of wormholes also on the CFT side. These are very exciting developments. Let me see where okay, sorry. So I have 2 more minutes. I wanted to make a comment on our own recent work on the global symmetry conjecture, also involving both instantons and wormholes, this paper, but I think I skipped that because my time is basically running out, and I'd rather let you read these 2 slides later on if you wish. The punchline is that there's again a very nice match between the wormhole argument and the instanton argument for how, with which strengths, global symmetries are violated. Global symmetries, by this I now mean not the Axion symmetry, but actual global symmetries which are linearly realized, which protect particles. Instead, let me advertise a recent, I think slightly crazy, but I mean very interesting, I feel, story that we tried to develop with these co-authors given here. So I'm thinking about the measure problem. Let's think for a moment about the measure problem of eternal inflation. Okay, so the point will be that I want to argue that topology change is unavoidable, it's necessary, also in 4D quantum gravity. So let me start by stating the cosmological central dogma, or what people sometimes call this, namely that the sister Hilbert space, which I also apply this to quasi-de Sitter-like inflation, has a finite dimension. So it is exponential of S of the entropy of the horizon, and this exponential is exponential of m Planck squared r squared, r being the de Sitter radius. You don't have to buy that. I mean, as we've seen before, Neil, for example, is not buying this, but let me for the moment accept this paradigm. So the idea is that if I live in the Sitter, really the horizon is for me the end of the world, and it's a quantum mechanical system of that size. So only the causal patch is real, and the ever-growing S3 of global de Sitter is unphysical. And let me draw this, give you this in the form of picture. So here I draw 2-dimensional de Sitter, Lorentzian de Sitter in the evolution, right? There's this one sphere of spatial selection blowing up, and the static patch is some strip of fixed size in physical units, and I'm only living here. And if tunneling happens, so I tunnel from one vacuum to another, then from the perspective of the static patch, it's just a quantum mechanical system changing from one minimum to another one, yet another one. Each time a tunneling happens, my system changes to another minimum, like a quantum mechanical particle. So now, oh, sorry, let me go back. So now the Wheeler-DeWitt wave function of the universe describes a static patch tunneling back and forth between different minima. Here again, this picture. But now I want to require a stationary solution. And a stationary solution has to be there in the presence of sinks, because this system has sinks, because I can also tunnel to ADS or Minkowski vacuum, from which, as far as I know, we don't come back to the Sitter. So now how do I get this? The only way that I see that you must allow for sources. And sources, of course, have been proposed, either Linde-Vilenki or Hartle-Hawking creation of universes out of nothing. And the claim here is that the picture of the universe in this setting is very simple. You have a finite quantum mechanical system for each de Sitter in your landscape, if you wish, and you have sources and sinks, and you have an eternal flow, and you can in principle calculate everything from a rate equation, which is in fact very similar to Vilenkin and Nomura's local measure. And in this context, crucially, topology change, an analogy to the baby universe or wormhole story described above, appears once again unavoidable. And of course, the punchline is that it's unavoidable on one hand and very poorly understood on the other. And that already brings me to my conclusions. Let me quickly go through them. So the gravity conjecture for axions demands certain minimal action instantons and hence certain minimal potentials. And Euclidean wormholes may be the universal semi-classical counterpart of those with gravity conjecture instantons, and the bound is made precise by this number. This number actually matters in inflation, in the strong CP problem, fuzzy dark matter. So one more point where it has recently been used in the context of axionic dark energy in this paper by Rodelius. Now, once you buy into these wormholes, of course, they come at a high price. The high price being this alpha vacuum and possibly other disasters, and conceivably understanding this will have to deeply change or affect our view of ADS CFT. And so a key question is whether and how topology change finds its way into our 4D quantum gravity. And my last point is that the Wheeler DeWitt view of the universe with a static patch, which I advertised before, seems to suggest that the answer should be positive, i.e. such topology change should not be ruled out. All right, thank you very much. That's it.
Thank you, Arthur. Okay, let's open the floor to any questions. Andre, please go ahead.
Yeah, thanks for the nice talk. So in this picture of baby universes and alpha parameters, is it important how these baby universes behave after they nucleate? If they expand or collapse immediately, does it change the conclusion?
So in the simplest calculation, which can be done, the one by Coleman, it does not, because these baby universes are simply the ways of cutting the Giddings-Schrödinger solution, which is a saddle point, which I simply use, and I sum over all such saddles. But then, as I said before, it is clear that this is not satisfactory, and one really should include this dynamics, and nobody knows how to do that. And properly, one should do it not just as dynamics as you described it, although of course our intuition is like that, but one should do it as a proper Wheeler-DeWitt wave function, which includes baby universes of all size. And so my personal picture would be to have a Wheeler-DeWitt solution with large spacetimes, universes of all sizes, and the Wheeler-DeWitt solution will automatically include the dynamics of these spheres growing or shrinking or whatever they do. Okay. But the problem is that nobody can do the calculation. What people have done, and that we will see some of this, is two-dimensional toy models, and recently three-dimensional toy models. One of these recent paper by Hartman, Maloney, and others, which I quoted 2 pages ago, argues for a 3 solution, but a slightly different type of wormholes.
Valerie is next.
I can't hear.
Please unmute yourself.
I think you need to unmute, Valerie. Maybe show your camera too. Yeah, great.
I just wanted to comment that there's a big difference between 2 dimensions and more, or in particular 4 dimensions. In 2 dimensions, you can think of branching off, say strings. Yeah. Strings can, split and branch off with the, roughly speaking, energy non-conservation, roughly speaking. However, in 4 dimensions, that doesn't seem possible. That does contradict locality, while in 2 dimensions it does not. So there is a very big difference between wormholes in 2 and higher dimensions.
I'm confused why you say it does not contradict. So I agree with you, but I don't understand why locality would not be a problem already in 2 dimensions.
Because if you have 2 dimensions, then you can construct. You can think of, let's say, you don't have sphere that surrounds the that surrounds the place where the wormhole branches off. Just Lorentzian process.
But the locality I was discussing about is different. It's because the wormhole connects at two different places. And people have argued that this issue...
The same very simple thing. Suppose you are an observer, right? You have a wormhole that branches off and takes out some matter, some energy.
Yes. No, sorry. It can never take out energy. Energy is gauged.
Oh, it can. In 2 dimensions, it can.
All right.
It cannot in 4, but it can.
But the Getting-Strominger solution does not, of course, contradict, and its interpretation by tunneling does not contradict energy conservation. I mean,
right.
Gauged quantities that do not go through the wormhole. It's only global symmetries that can be violated, not gauged ones.
No. What I'm saying is that you can think of real branch of taking away energy, all this, and violate the coherence. I don't think. I think the problem that I was alluding to arise at a final level. So I accept that it's understood, as Getting-Strominger's second paper or so and later papers proved, that there's no problem with quantum mechanics, coherence, locality, energy, and so on at this level. But only for, not in 2.
Also in 4. So okay, good.
No, I'm saying that in 2 dimensions you do have loss of coherence.
Okay, possible. Let me not argue. Let's hear the other question maybe. Yeah. Let's discuss later in detail. I'd like to understand better.
Alex, I think you're next.
You argued that in order to have a stationary solution to Wheeler-DeWitt equation, there should be source terms in the presence of sinks. And I'm wondering about the form of these source terms. For example, if you think of this creation of universe from nothing as being a source of these new universes, should the source term be regarded as an amplitude for a universe of 0 size? Or what is... and then there should be inverse transitions from the universe of finite size collapsing to that.
So the solution. So of course, once there is a solution, so the Wheeler-DeWitt equation, of course, have different solutions. So we are in a way, what we worked this out to a certain extent in our recent paper. So I cannot report. I was too short to report the details. But what we simply enforce boundary conditions at the moment by hand. It has to be seen how one can derive them, that the sinks are really only sinks, and then the sources have to be only sources. Of course, in principle, the reverse solution then must also exist. But the question is which solution of the Wheeler-DeWitt equation describes the universe, and our proposal is, which I think is kind of a quantum mechanical version of your proposal of local measure. That you should think of a wave function which flows only in one direction from sink to source, in this way populating, in principle, all possible vector, either through direct creation or through tunneling processes, and always ending in terminals. And we only put it in by hand at the moment. But I think if you look at, for example, concrete calculations, the Hartley-Hawking paper, I'm not saying this is the right proposal, but there, of course, explicitly, you have a source at 0 volume. However, our model, the level of the model here is that our de Sitter is a finite quantum mechanical system, and basically the whole process of the 0-size sphere being created and then growing to beyond the horizon. All of this is modeled for me at the moment as being the source. Okay, so in this picture, the process of this 0-size nucleating 3-sphere and its growth to horizon size is the process of encoded in the source. So this should clearly be understood much better.
Valerie, did you have a follow-up question, or is your hand just raised?
I'm happy to discuss further with Valerie if he wants to add to this 2D, 4D story.
Yes.
If there's still time, I don't know.
I don't know if you have a follow-up, Valerie.
He's still muted.
He's still muted.
No, I just forgot to.
Ah, fine, no problem. Okay. Any other questions? If not, let's thank Arthur for a very nice talk.
Thank you.
We can talk later on.
Yeah, thank you. I would like to hear your complaint in detail. Yeah, thank you.
Okay.
Thank you very much. Okay, our next talk is Dvali. And he's going to tell us about gravity and Axion.
Can I share the screen?
You should be able to. I made you co-host.
Let me see.
So Gia, I will prod you after half an hour, if that's okay.
Great, thank you. Now you see nothing. No share. Okay. Okay, I think you see the screen now, right?
Yes, that's good.
Okay. I would like to thank organizers for the invitation, and I also would like to join the solidarity with all the people opposing this senseless war on Ukraine, and in particular our colleagues in Russia that oppose the war. Now coming back to physics, so I'm going to discuss certain interesting implications for Axion and for the vacuum structure. And I'm going to tell you something that sounds very interesting and also intriguing, and sounds like pretty powerful as a conclusion. So the conclusion is that gravity demands that every gauge sector, so in order to couple consistently gauge theory, non-abelian gauge, asymptotically free gauge theory, with gravity, it requires an axion. So axion is a necessary condition for coupling a non-abelian gauge sector to gravity. Okay. Now here are some of the basic papers on this. So this is like putting together several things and also reviewing relatively old results. Now let me make a sort of an outline in the summary. So the basic point, and also the messages that I want you to take from this talk. So the first thing is that the S matrix formulation of gravity, of quantum gravity, which is basically the only formulation that we know at the moment, and it's very likely that whatever alternative formulation there can exist, it also should boil down to this. It should respect S matrix. So that excludes the Sitter vacuum in particular, both stable and metastable, but more than that, and this has highly profound consequences for gauge sectors and for the field content of the theory. So the most convenient language is to discuss this from the point of view of forms. So in particular, this excludes any massless free forms from the theory. And this automatically implies that theta vacua for arbitrary gauge sector must be unphysical. Okay, so we cannot have a gauge sector with non-trivial theta vacuum. And this a necessary condition, therefore, for any gauge sector is existence of an axion. It's a necessary condition. Now, this raises the question, of course, and what is very important is that the shift symmetry of the axion should be exact. So not only the gravity demands existence of the axion per gauge sector, but also it imposes this condition that the shift symmetry of the axion, of each axion, should be exclusively broken by the topological susceptibility of that sector. Okay, and so this raises a question which is naturally answered by the dual formulation of gravity in terms of a gauge two form. And this has pretty interesting consequences, because one of the consequences, this implies that the scale of the axion is related with the scale of gravity. Okay, and I will explain this now. So now as I said, the S-matrix formulation is currently the only known formulation for quantum gravity. We don't have anything else. And in particular, this is organic in string theory. And there are pretty simple arguments that show that therefore this excludes any de Sitter type vacuum, either stable or metastable, or actually any state of any potential of a scalar field that is eternally inflating. So therefore, in this discussion, and so now I will try to understand. So you can find there are simple scaling arguments to show this. Surprisingly, I've never seen these arguments earlier in the literature. There are very simple scaling arguments that show why quantum gravity is special. So formulating, for example, QCD within de Sitter is not an issue. So asymptotically free theories we can formulate within de Sitter. S-matrix formulation, at least as a limit. The issue is strictly about quantum gravity. So I will take this as a point. If there will be questions, of course, I'll be happy to answer. And explore consequences for gauge sectors. So therefore, I will base, let's see what this implies for the gauge sectors. So the framework that I will be working in, there will be 3 + 1 dimensional effective field theory of S-matrix defined on asymptotically S-matrix vacuum of Minkowski. Okay, so this is the framework. And so the question is, what does this framework imply for gauge sectors of the theory? So the consequences are pretty interesting. Immediately, you conclude that there cannot exist in such a theory of gravity, there cannot exist any massless free forms. Why? Because the massless free forms, no matter whether they are elementary or composite, it doesn't matter where they come from. Gauge invariance implies that the moment you have a massless free form in theory, which transforms under a gauge shift, where omega here is a 2 form, this is a standard gauge transformation of a massless free form, and E is the invariant gauge invariant field strength. Okay. Immediately, this implies that there are infinite number of vacua which obey the superselection rule. Okay. So why? Because the equations of motion, because the massless free form doesn't propagate any degrees of freedom, and the equations of motion they just simply reduce to the one which has unique solution as with a constant, uniform, constant field strength, the electric field. And there are no transition between these different values of the electric field. In other words, there are infinite set of vacua with no transitions among themselves, among each other. And so there are huge number of superselection sectors. Now, a continuum of superselection sectors. Now, the thing is that the energy density necessarily depends on this field strength. And this means that we have superselection sectors with different energy densities, okay? With no possibility to relax. Now, this is true for arbitrary form of the Lagrangian. So if you write down an arbitrary gauge invariant form of the Lagrangian, that just boils down to, in the vacuum limit, it boils down to an algebraic function of E, and the same follows. So there are these superselection sectors, and necessarily some of those, it is impossible that all of those superselection sectors satisfy our criterion of the S-matrix. Because if you choose one to be asymptotically Minkowski, there would necessarily be some other sector that will not be asymptotically Minkowski, will be de Sitter. Now, there can be sources. Now, the 3 forms that is well known, they can couple to sources. And as long as you introduce massive sources, for example, 2 branes or axionic domain walls, they are nice examples of sources or 3 forms. Sources, they allow transitions. So by nucleating bubbles of two branes, domain walls, we can have transitions among the selected discrete set of vacua. But this doesn't eliminate superselection among others. So therefore, having massive sources doesn't eliminate this story. So this means that the conclusion is that the existence of a massless free-form, either elementary or composite, is incompatible with the S matrix criterion. Okay. This means that per every free-form, we must have an Axion degree of freedom. Why? Because Axion is the only gauge invariant possibility for giving a mass to a free-form. Okay. And you can see this from this very simple Lagrangian. So here I have introduced Axion. This is Axion is A, and coupling with the free-form field strength. For simplicity, I just choose quadratic function. It doesn't change anything. And you can see very easily that if you integrate out the Axion degree of freedom, you end up with a unique vacuum with zero electric field strength, because Axion gives a mass to a free-form. So once we couple Axion to a would-be massless free-form to an Axion, the theory becomes equivalent to a massive pseudoscalar or a massive free-form. The same thing. Okay. All right. Now, this has very profound implications for gauge sectors, and this is very important of gauge theories. Why? Because so we know that in gauge sectors we have theta vacua. Okay, so if we have confining gauge theories or even gauge theories in the Higgs space, we have theta vacua, unless we have axions or massless quarks, which is the same thing. I come back to that. Now the point is that the theta vacua are fully equivalent to the vacua of a free-form. And the dictionary is goes through the Chern-Simons free-form of the gauge field. There is no assumption here. So if you have a non-abelian gauge theory, you have a free-form. Okay, this free-form, of course, is a composite operator. Okay, so far it's a composite operator, and it shifts under the gauge transformation. So the moment you do QCD gauge transformation, this free-form shifts, I mean, as it should, as an antisymmetric derivative of a two-form, where the two-form is given by this, where omegas are gauge transformation parameters of QCD. Now we know this. Now, what this has to do with a massless free-form, and here is the very important step. Now the point is that because of the topological structure of the non-abelian gauge theories, we have non-zero topological susceptibility of the vacuum. In other words, non-zero topological susceptibility implies that there is a correlator. This is well known. I mean, we know that there is a correlator. This correlator in QCD is non-zero. It's a non-zero number. And this correlator, existence of this correlator, is in one-to-one correspondence with the existence of a massless free-form. Here's why: because this correlator, because E is a derivative of C, having this correlator constant, Q is the form momentum. So in the zero limit of form momentum, this correlator is constant. This implies that the CC correlator, the same type of correlator, CC, has a pole at Q squared equals 0. This just follows from the spectral representation, okay, of the correlator. There is no way out. So once we have topological susceptibility of the vacuum, this implies that there is a massless free-form in the theory. And then my argument follows. So this means that the Chern-Simons free-form of a non-abelian gauge theory necessarily contains a massless free-form if there is non-trivial topological susceptibility, and plus a massive tower. But the massive tower doesn't play any role in the vacuum structure of the theory, because occupation number of massive modes in the vacuum state vanishes. And so therefore the statement is exact. So regardless what is the UV completion of your theory, if there is a topological susceptibility of the vacuum, this immediately implies that there's a massless free form. This immediately implies that you have theta vacua. So the theta vacua, the normal theta, the familiar theta vacua that we are all familiar with, they are nothing but the vacua with the constant electric field, uniform electric field of a Chern-Simons free form. Okay. Now, this is what I offered you at this point is just interpretation of the old result. We know that there are theta vacua in QCD in the new language. But why is this so very important? Because language matters, as we know. Why? Because the language of topological susceptibility is most powerful for my purposes because it is completely independent of what saturates this correlator. So you have a gauge theory, and for me, it's sufficient that you tell me you have a gauge theory with non-zero topological susceptibility. The states that saturate this correlator could be instantons. In the standard discussion, we discuss instantons, but by no means instantons are the only contribution to the topological susceptibility of the vacuum. Could be tower of black holes, whatever you want, okay? So, and this is what makes it very powerful, because I don't even need to know what saturates this correlator in order to draw these conclusions. All I have to know that this correlator is non-zero, which is in standard gauge theories. So therefore, we need to, by consistency, we need to introduce an axiom per each gauge sector. By the way, massless quark also eliminates topological susceptibility of the vacuum, but I'm not making any distinction between the case of massless quark and an axion, because when you have massless quark, I've shown this some time ago, that when you have massless quarks, the story is the same as the axion. What happens is that eta prime plays the role of the axion in that case. So it's the same axion physics. Now, so therefore, this means that the S-matrix formulation of gravity demands that every gauge sector comes together with the axion, okay, or a massless quark, which is the same thing as I said. But what is very important is that this shift symmetry of the axion cannot be broken by any additional source, only by the topological susceptibility of that sector. So each axion should get a mass only by Higgsing a corresponding Chern-Simons free form. And this sounds like a miracle. So this is a necessary condition. This is what gravity is telling you. I didn't make any assumptions. I only assumed this matrix formulation. So immediately we get that this is a necessary condition, but it sounds like a miracle because normally we say, okay, global symmetries, I mean, they don't have any particular reason to be respected. They may be respected, but they don't have any particular reason to be respected by gravity. So this cries for some explanation because, of course, I mean, we cannot exclude miracles in quantum field theory, but usually when there are miracles, there is a good reason. There is some accompanying reason for these miracles. I mean, miracles do not happen for no reason. And here comes this distinction between the pseudoscalar formulation of axion and the two-form formulation of the axion. Now, there exists a dual formulation for axion, of QCD axion. I'm talking about QCD axion, full-fledged dual formulation of QCD axion in terms of an antisymmetric two-form. So B mu nu, here is the Lagrangian, full QCD Lagrangian of that formulation. Now, previously in the literature, I mean, people thought that this formulation was not possible for QCD axion. And the reason was that people thought that the axion potential that is generated by QCD necessarily breaks duality between the pseudoscalar formulation and B mu nu formulation. And I showed that that's not true. Actually, the caveat was that the potential for the B mu nu axion comes from the gauge kinetic function of the Chern-Simons free form and not from the potential of the axion. So therefore, there is a full-fledged dual formulation of QCD axion in form of an antisymmetric two-form. Now, why is this formulation more powerful? Because there is no global shift symmetry in this formulation. In this formulation, what happens is that there is an antisymmetric two-form that shifts under the Qcd gauge transformation. So the moment you do perform Qcd gauge transformation on gluons, this form shifts. And so in this formulation, again, topological susceptibility is removed, theta vacuum are removed, and the vacuum of the Qcd is exactly conserving without any topological, without any non-trivial theta vacuum. Now, you can, it's a simple exercise to prove that this formulation is exact dual to the pseudoscalar formulation, except that it explains the miracle why there is no explicit breaking of shift symmetry for the axiom. Okay. Now, but there is no free lunch, of course. In other words, so what we understood so far is that there are two formulations of the axiom in terms of a pseudoscalar and anti-symmetric two form. And they are at the level of effective field theory, they are exact dual. They are fully equivalent. However, they differ by UV completion of the theory. In particular, one is relying on this mysterious global symmetry, but the other one has no global symmetry, it only has gauge symmetry. And but the power of gauge redundancy is telling us that this gauge symmetry, of course, cannot be broken, obviously. So this explains the miracle. Now the question is, in this language, how can I understand what could undo the masslessness, the massiveness of the Qcd free form? And there is only one way. In order to create a problem of the Sitter vacua in Qcd, we have to unhiggs the free form. And unhiggsing of free form is only possible if you have another free form. So somehow, a dangerous theory, so let's say, if you say, okay, I have this dual formulation of the axiom, and now somehow I have some unknown physics, ultraviolet physics. And in the pseudoscalar formulation, it would say, oh, look, this ultraviolet physics could simply break my shift symmetry. But in the mu formulation, you know that this unknown physics, the only way for the unknown ultraviolet physics to create a problem is to provide another free form, another would-be massless free form. Okay, gravity has a candidate in form of a Chern-Simons free form of gravity. Sure, so there is this candidate in gravity of Chern-Simons free form, gravitational Chern-Simons free form. But the question is, does this gravitational Chern-Simons free form contain a massless free form? In pure gravity, so this depends whether in pure gravity, there is a topological susceptibility of the vacuum, whether this correlator is non-zero. I mean, currently this is not known. I gave some arguments why in pure gravity, topological susceptibility is expected to be non-zero based on black hole tower of intermediate virtual black holes. I even estimated the possible strength, but it's not known. However, what is known from this S-matrix argument is the following, that if gravity potentially, if in pure gravity, potentially there is this correlator, then by S-matrix formulation demands that gravity should come together with its own axiom, should not disturb Qcd axiom, because otherwise we will create a problem with the S-matrix formulation of gravity. So gravity should come either with its own axiom or a chiral fermion. By the way, there is a very interesting possibility of neutrino playing the role of that protective chiral fermion, because if one of the neutrinos without gravity is massless, then there is a chiral symmetry which removes topological susceptibility of the vacuum in gravitational sector. And so in that way, there is no topological susceptibility in gravity. And as a bonus, one of the neutrinos, at least one of the neutrinos, or maybe all of them, they get masses from the chiral anomaly, from the gravitational chiral anomaly. And on its own, this is a very interesting possibility. But the bottom line is the following: no matter what, with or without topological susceptibility in pure gravity, at the end of the day, gravity should not disturb Qcd axiom. So gravity demands that there is axiom, because in Qcd, for sure, we know that there is a topological susceptibility. We have at least one source that indicates that these are instantons. So we know at least there is a contribution from instantons. In large M Qcd, we know that there is an additional sort of story. So we know that in pure glue, there is a topological susceptibility, which means that no matter what, if we embed pure glue or glue with massive quarks within gravity, within a symmetric formulation of gravity, this must be coupled to an axiom. So this is a necessary condition. So therefore, the Qcd axiom is safe by the asymmetric formulation of gravity. And the natural way of realizing this Qcd axiom is through the antisymmetric B-mu form, because antisymmetric B-mu form carries itself this gauge symmetry that is self-protective. Okay? You cannot simply just write down a term in the Lagrangian which breaks the gauge symmetry. That's not possible. And this is extremely important. Now, in order to, I'm nearing my conclusion. So what is this story, therefore, to summarize? What we are learning is the following, that the moment you embed a gauge theory to gravity, the theta vacuum must be eliminated. This means that gauge sector can be embedded into gravity only together with massless quarks or together with the axiom. Now, in ordinary QCD, we don't have massless quarks. At least this is what our lattice friends are telling us. Correspondingly, the axiom is a necessary condition for embedding our ordinary QCD into gravity. Now, the vacuum of QCD, also gravity tells us that must be exactly CP conserving. At the level of course, as I said, there is nothing wrong in postulating that there is a Pechequin type of ultraviolet completion for gravity, for the axion, in which axion becomes a phase of a complex scalar. But this condition that this complex scalar must have a global symmetry, which is exact to all orders in the field expansion, that looks like a miracle. So therefore, if you ask me, it's much more natural that actually the axion is realized not through as a pseudoscalar realization, not to pseudoscalar version, but through B-mu version. Now, there is a bonus that is coming from there. I mean, there is a price to pay, which is also a good price. Because once we say that, okay, axion is realized through B-mu gauge formulation, first, the protection becomes immediate. And secondly, for B-mu formulation, doesn't exist any UV completion within effective field theory. So B-mu formulation has UV completion directly in quantum theory of gravity. This is very interesting because somehow gravity is telling us, this is also natural because it tells you that, look, gravity, the axion originates from gravity because it's a necessary ingredient of gravity. A priori, QCD had no reason to have an axion because there was no problem in CP violation in QCD. What's the problem? I mean, nature doesn't require CP exactness in gauge sector. So axion, it's a natural thing that axion is coming from gravity. And therefore, it is also natural to think, it's almost mandatory to think that the scale of axion is related with the scale of gravity. In other words, in the limit, when we take M Planck to infinity, axion can decouple, okay? There is no problem with that. Axion can decouple in that limit. And this indicates that there is a correlation between the axion scale of axion and the Planck mass. Now, this is my last transparency, and I can simply tell you that, so the question is, okay, I have two quantities, the scale of axion and the Planck scale. And what I know is that for any finite M Planck, FA must be finite. There is this correlation between the two, okay? Now, how are the two related? Okay, if FA is analytic in M Planck, the simplest relation, if you ask me, would be that FA is M Planck up to some numerical coefficient. That sounds to me the most natural story. Now, the question is, what does this imply for the experimental searches for the axion? Now, of course, the coefficient is order 1. These are not good news for the direct experimental searches for the axion because it's very hard to look for directly for the axion with Planck scale decay constant. But nature is whatever it is. We cannot, I mean, nature should not care about our comfort or in experimental searches. This is one thing. So therefore, I mean, so we have to understand nature, and that's it. But also, it could be that this intermediate coefficient, which relates the Axion scale to the Planck scale, is somewhat suppressed. That could be by additional factors. And so this is why it's extremely important to understand this relation, okay? Now, this relation cannot be understood at the language of effective field theory, at the level of effective field theory. So it requires more explicit computation within framework of quantum gravity. So I'm going to end up on this optimistic note that good news is that we know that since there is gravity and there is standard model and there is Qcd in the standard model, there is at least one new degree of freedom beyond the standard model. I hope Neil can tolerate this one more degree of freedom, okay? But that's a necessary condition. Okay, so thank you, and yeah, I finish on this optimistic note.
Thanks very much, Gia. Open to any questions? Misha.
Yeah, hi there. Question. So our universe is now expanding with acceleration. And so according to you, this is kind of not possible. And I wonder what is the resolution of this puzzle.
Yeah, Misha, thank you for a very good question. Actually, of course, I didn't have time to discuss other implications of this for cosmology. The implication is that, no, it's certainly possible that the universe is accelerating. My prediction is that dark matter cannot be a cosmological constant. So there is so what the S-matrix formulation of gravity is telling us is that there are certain fixed number of upper bounds on the number of e-foldings that any inflation can last, okay? So correspondingly, the prediction is that dark energy, yes, cannot be a cosmological constant, which again I consider as good news because if dark energy were a cosmological constant, life would be very boring because you just write a constant and that's it. It explains everything. Now, what S-matrix formulation of gravity is telling us, this is not possible. So correspondingly, whatever dark energy is coming from are either new degrees of freedom, like for example, quintessence field or a scalar field that is rolling slowly. There is no problem with that. So as long as the expansion of the universe is not eternal, as long as we are not entering in eternally inflating phase, eternally inflating phase is widely discussed. Alex Delengin, Linde, these people were, of course, discussing this phase, but this is what the S-matrix formulation is telling us. We cannot be entering in eternally inflating phase. As long as the number of e-foldings that we have is less than the bound, we can discuss the bound separately. I mean, if there are questions, I can present what the bound is. Then there is no problem. So actually, my prediction is that we don't see, it's not lambda what we are observing. It's some kind of new degree of freedom that has an energy density that changes in time. And there is an upper bound of how long this expansion can last.
But this is a new degree of freedom, which is not axial. So this is the one which is not tolerated by Neil, right?
Well, I mean, okay. I mean, this was a joke, obviously. I don't see why Neil should have a problem with a few other degrees of freedom. Okay,
I don't have a problem, but there's a penalty.
Right, there's a penalty, sure. Look, I mean, jokes aside, I fully agree with Neil that we should be minimalistic, that I fully share this, okay? That's why in my presentation, I was absolutely minimalistic. I'm not assuming anything beyond what we know, and this condition that Axion must be there, and that dark energy cannot be a constant, this is imposed upon me by this fundamental principle of S-matrix. So this was
so Gia, let me just interrupt there. Can you say a few words to explain why you are so impressed by the S-matrix? I mean, from a real physics point of view, nobody ever saw an S-matrix in any situation. experiments are always done in finite size apparatus. Nobody
Absolutely.
ever saw an asymptotic state. Why should we take S matrices so seriously?
Right. So no, this is a key question. Of course, this is a key question. So now the thing. So what I'm taking. So by the way, I'm not saying that I'm very happy that the S matrix is necessarily imposed upon us. What I'm saying is the following: that in quantum gravity, the way we know it, okay, the fully fledged quantum formulation of the theory, we only know how to formulate it as according to the S matrix rules. Okay. So in other words, you see, in gauge theory, we have alternative formulations. In gauge theory, S matrix is a tool, but it's not a fundamentally important formulation of the theory. For example, we have world identities and other things. Now the problem is, and string theory, I'm not hung up on string theory, but string theory is a good representative because it makes this very explicit. So in string theory, this is explicit. We don't have we don't have Hamiltonian, we don't have world identities. So the string theory as a theory is formulated according to S matrix rules. Okay. Now people are also formulating string field theories, but those are, so the state of art is that every time we have some sort of different formulation, that's always a limit in which closed strings decouple. So the issue is really with gravity, because in string theory, gravity comes from closed strings. And so it looks like that with the current understanding of quantum gravity, S matrix is simply a formulation. Now, of course, it's an interesting philosophical question. Can a theory which is formulated through the S matrix offer a vacuum on which S matrix is not defined? Okay, so of course, in my discussion, I was assuming that that's not possible. That's an additional discussion. We can. So sure, I'm open to that discussion. In other words, one can say, okay, let me take this formulation of the theory as formulation, but maybe tomorrow we're gonna learn how to formulate theory on the sitter and take it from there. That's perfectly fine. And of course, I'm thinking a lot about that, how to formulate theory on the sitter, etc. But what I'm saying is that in our current understanding, we need to formulate theory on an S matrix vacuum. And that's great, because then theory becomes more constraining. And so what we are learning is that everything that we call the sitter or cosmology is not a vacuum, but an excited state on an S matrix vacuum. So, which, by the way, resonates what you are saying. You were saying in your talk, because the past of the universe is just an excited state on the vacuum. Okay, and so that's the picture. So, and this picture is self-consistent, and so that's what it gives us. Okay.
Great, thank you very much. I want to let Andre and Arthur ask their questions.
Yeah, thanks. So just to clarify, so in your argument about virtual black holes giving rise to non-zero R dual, do these virtual black holes have to be Kerr black holes? And if yes, what's a typical spin to mass ratio?
Yeah, so the virtual black holes that I meant in this correlator, let me go to the correlator. So I've estimated, it was just an estimate. So sorry, but not this one. Yeah, so yeah, the question I tried to ask was, okay, I mean, if I have pure gravity with just simply massless spin 2, gravity discussed as EFT, massless spin 2, and nothing else, no other massless degrees of freedom, okay? Everybody else as massive. So whether in pure gravity, topological susceptibility is non-zero, okay? This question has never been answered. In general, it's extremely hard to compute topological susceptibility because it's a non-perturbative quantity. However, I gave arguments why virtual black holes are one source, realistic source, that they can saturate this correlator. And the argument is that, you see, if you are familiar with there is this beautiful work by Witten and Veneziano about mass of the eta prime in large N QCD. And in large N QCD, what happens is that you can forget about instantons. That's why the language is extremely powerful. And you can think in terms of topological susceptibility. And in that language, of course, there is only glue ball tower. So you have infinite tower of glue balls. And so it is, in that language, it is that tower that saturates the correlator, okay? Because you can bypass the discussion of the instantons, okay? Now, the black hole tower in my language, because I have this picture of black holes as composites of gravitons, okay? So in that picture, black hole tower is extremely reminiscent of global tower in large QCD, okay? And so therefore, the natural connection was, yes, if I can think in terms of global tower, in QCD saturating this correlator and giving non-zero correlator, then it's natural that somehow similar thing may be happening for black hole tower. And of course, in black hole tower, you include all possible black holes, of course, as virtual states, obviously. Of course, Kerr black holes and black holes with corresponding quantum numbers, of course, because this virtual black hole has to absorb RR dual. And then, so now the thing is that you can estimate the part of that tower, and that's very interesting. You can estimate the contribution from the part of the tower that is still semi-classical. And actually that contribution gives exponent minus number of particle species in the theory. So if it's only standard model, it will be like exponent minus 100 or something like that. Okay. Now, of course, here, as usual, we are looking under the lamp. So we are computing the part of the spectrum that we can handle. Of course, there may be additional contributions, etc. That's why I'm saying that the issue about topological susceptibility in gravity is an open issue. So maybe it's simply 0, and then we don't need to worry. And yeah. But this is, yes, the tower should include Kerr black holes, and moreover black holes with relevant quantum numbers that can absorb RR dual. Yeah.
Okay, great. Thank you. Last question, Arthur.
I actually have only a very brief comment. I want to defend the free or massless three-form theory. Namely, I want to start from a theory with a zero-form field strength, where there's just a discretum of vacua connected by domain walls. And this theory does not have the problem of any superselection states. I mean, they're just discrete vacua, and you can go from one to the other by passing through domain wall, nothing else. I claim, and I don't.
You mean degenerate vacua?
No, non-degenerate. Quadratic potential.
Then those are excluded by the symmetry criterion.
No, wait a second. There are domain walls, and the domain walls are light enough so I can tunnel from one to the other quickly.
No, what I'm saying is that, but you are already killing my starting point, because I'm saying.
Yes, exactly. That was exactly my intention.
You are not killing it. You are
let me finish. Let me finish my point. This theory, the theory I'm describing, is exactly the dual theory to a massless three-form.
That's why it's excluded. That's why it's excluded. In other words, what I'm saying that S-matrix criterion excludes any non-degenerate vacuum states, because if one is S-matrix, the other one cannot be S-matrix. There is one exception of.
I have light domain walls, which quickly.
Wait a minute. Look, I'm saying S-matrix criterion excludes non-degenerate vacua separated by a barrier. Why? Because if one is S-matrix, the other one cannot be S-matrix, because the inflation will be eternal in the other one. There is one exception. No, this is my starting point.
It's a light domain wall, it decays. The higher vacua quickly decays.
No, doesn't matter how fast it decays, the inflation is eternal. If inflation is not eternal, no, this is important. No, let me see. Here is the mistake you're making. No, let me clarify this. This is extremely important, because look, in the literature you can find, and probably this is what you are alluding to, sometimes people say, okay, I have a vacuum, and I can make decay of the vacuum to be sufficiently fast so that inflation is not eternal.
Yes.
Then you are working in the domain which is no longer applicable, because tunneling process is by default when the action is larger than 1, because otherwise WKB approximation breaks down, and you have to consider 1 over S corrections, which are more important than exponent minus S corrections. This is the typical mistake a lot of people are making in the literature, and this is extremely important to understand, that the validity of the tunneling approximation means that the action is large. And whenever tunneling approximation is valid, the vacuum lifetime of the vacuum exceeds the S-matrix bound. So this is very important. Thanks for bringing this question, because this is extremely important. That's why that's not a loophole. Right.
Okay, I think this discussion will probably continue. So let me encourage you to continue it in the break. And the next speaker is Christof Wetterich. Oh, let's thank Gia for a fascinating talk.
Thank you.
Great. So Christof is ready, and he's going to tell us about quantum gravity from the beginning to the present universe. Just a small topic.
So you can hear me?
Yes, it's good.
Okay, fine. Now, so sorry, something is wrong here. And we'll be at the beginning in the moment.
Okay.
So my task today is to convince you that quantum gravity can actually predict important things in cosmology. It can predict important features of the effective scalar potential as you need it for inflation or dynamical dark energy or many other things. So I know it's a hard task because many of you will say, okay, we do not have any valid theory of quantum gravity. How can it be predictive? And will be quite skeptical about it. For those of you, at least, I want to remove some of the prejudices that you may have what is natural or not natural. So let me start and try to convince you that actually you can do computations in quantum gravity, you get results, and you have to live with them, in my view. Quantum gravity, what is it about? It's about fluctuations. It's about the fluctuations of the metric. That's, for me, the key of quantum, because otherwise you have a classical field theory. So whenever you speak about quantum gravity, you better have a theory that the method that can take them into account. And I will present you computations of the effects of graviton fluctuations on the potential. And sometimes I'm going to my string colleagues and ask them, what is string theory telling about it? Is this effect there? Is it not there? And then the answer is we don't know, because we do not have a quantum field theory of string theory. And I think that should teach you that a certain modesty is perhaps required when you think about the big claims that the theory of quantum gravity is there. You should at least be able to give answers to simple questions. Let's say, is this effect of metric fluctuations on the scalar potential real, or is it not real? Is it wrong, or is it right? So let's start. I will be rather simple-minded. After all, gravity is a field theory, similar to electrodynamics, just a metric field instead of the photon field. Gravity is a gauge theory, similar to QED or Qcd. The gauge symmetry is general coordinate transformations or diffeomorphism. So when you think about quantum theory of gravity, it's just a way of including the metric fluctuations in a functional integral. From that point of view, gravity is pretty similar to other quantum field theories. There's not such a big difference as people sometimes seem to think. You could say the metric is a tensor, gauge bosons are vectors. That's true. It's a minor difference. Actually, if you formulate things in terms of the Vierbein, then it's even vectors. So that's not really important. What is important is quantum gravity is not perturbatively renormalizable. That's a very important fact. And it has to do, you see that to a certain extent, if you look at low energy gravity, then you have a type of effective coupling, which is momentum squared over the Planck mass squared, which is tiny for present energies. But when you go close to the Planck mass, that becomes huge, and then it seems even to diverge. So you have to deal with this situation. So actually, quantum gravity is not perturbatively renormalizable, but I think it's actually non-perturbatively renormalizable. That goes under the name of asymptotic safety. The idea goes back to Steve Weinberg, but only with the pioneering work of Martin Reuter, it has become possible to do actual calculations in this setting. And of course, one has to use functional renormalization, as I will also underline at certain other points. But except that, asymptotic safety is not such a big deal. I mean, somehow most of you are used to perturbation theory. It seems a strange thing, but if I talk to my solid state friends, they tell me, so what's the matter? All of our fixed points are actually with a non-zero coupling, because that's the difference. For asymptotic freedom, you need an ultraviolet fixed point at zero coupling, and then you can do perturbation theory. But if your fixed point is not at zero, then in general, you have not a small coupling. You cannot do perturbation theory. But as I told you, that's quite common for most other problems except particle physics. The fixed points that are dealt with, the Wilson-Fisher fixed point or so on, have non-zero couplings. And this is simply, in my view, the case for quantum gravity. So we have to deal with flowing couplings, actually flowing functions in a moment. And we need to introduce a renormalization scale. I call it K, and it's introduced such that only fluctuations with momenta bigger than K are included, and those with momenta smaller than K are not yet included. So K can be external momenta, geometric quantities, all that is difficult. I actually will just introduce K as a scale in the formalism by hand, by having a theory with a functional integral with an infrared cutoff, and then you remove it at the end. Also, when K is diverging, then the cutoff is diverging. That means there is no fluctuation included. We start with some type of classical action or microscopic action. And then when K is zero, you have all fluctuations included, and you get the quantum effective action. So when you slide down K from very large value to zero, you gradually include all quantum fluctuations. So that's the essence of functional renormalization. Now let me give a warm-up example, which is the quartic coupling in the standard model. So Higgs potential quartic coupling, lambda that you have here. And now let's see what do the quantum gravity effects to lambda. It's pretty simple. They induce an anomalous dimension. So you get a term in the flow equation for lambda, which is proportional to lambda, and A is this gravity-induced anomalous dimension, which is actually positive. So if you go for a moment to the limit of constant A, then of course there's a very simple solution of this flow equation, namely lambda goes to zero with the power K to the power A. So when K goes to zero, lambda goes to zero. That's a very general and simple result. And it tells you that quantum gravity flattens the scalar potential. That's the general effect of the metric fluctuations. It's not particularly complicated. That's it. Now, in this language of relevant and irrelevant couplings, you see that the quartic coupling lambda, in this case, it flows towards zero as your infrared cutoff is lowered, as you include more and more of the fluctuation. That's the case of a so-called irrelevant coupling. And if your theory is to be completed to infinitely short distance scales or infinitely high K, that means that this coupling is predicted to be at the fixed point. So that's a general setting for the so-called irrelevant coupling. So quantum gravity, if it would be alone with the scalar field, would simply predict that the quartic scalar coupling is zero. Now things are a bit more complicated, because if you look at a concrete formula, here I have it, you see this A is really computable. There are definite numbers associated to it. You see there's one important quantity, and that is this 1 over mp tilde squared. And mp tilde squared is just the squared Planck mass divided by k squared. So when k gets much smaller than the Planck mass, then this A gets quickly to zero. That simply tells you that the gravity effects decouple below the Planck mass. Very natural, very simple. And actually what happens when you have a fixed point for asymptotic safety, that means that this mp tilde squared actually goes to a constant. So the scale-dependent Planck mass will scale proportional to k squared, which is the only scale in that which is natural for an ultraviolet fixed point. So you have gravity domination as long as your scale is of the order of the Planck mass or beyond, and then gravity decouples. This is a simple picture, and actually this gives a prediction for the standard model. So you have a prediction that near the Planck mass, the quartic scalar coupling is 0. Then there are still small effects of gauge boson fluctuations and so on that drive it to bigger values. And if you assume that your standard model is just valid up to the Planck scale or has only very small modifications, well, you get a prediction that Misha and me like quite a lot, because it was a prediction of the Higgs mass, which was pretty good, and it was a real prediction. So it's an example that quantum gravity can give you predictions for particle physics. This will not be my topic today. My topic will be predictions for cosmology, predictions on the scalar potential. So that was just a warm-up example. And now we go to scaling solutions. So this is not predicting only a single coupling or a few couplings. This is predicting whole functions as the scalar potential, which is a function of the scalar field phi. So starting at an ultraviolet fixed point, we run with the scale k to 0 at the end. And if you want to have an ultraviolet fixed point, you should have such scaling solutions. Scaling solution means that dimensionless functions expressed in terms of dimensionless fields do not depend on the scale k. So again, this is not something I invent. In solid state physics, that's called the Widom scaling equation and so on. So it's a very general concept that you predict not only one coupling or few couplings, you predict whole functions. Or simply because if you would express it in terms of a polynomial expansion, then we would have phi to the 6, phi to the 8, phi to the 10. All these are irrelevant couplings, and all those are predicted. So in general, you flow then away from the fixed point and you get relevant parameters, but they will not be my topic today. I will really stick to these scaling solutions because actually that's only those that you need, and you can even stay on the scaling solutions. So at these scaling solutions, there are fixed values for infinitely many couplings, or there are fixed functions of dimensionless fields. And of course, in order to compute that, now it's pretty clear, you need functional flow equations that tell you how whole functions change with scale. Scaling solutions are solutions of nonlinear differential equations. And you know there are not too many of them in general. So it's the solutions of nonlinear differential equations that are valid, let's say, from scalar field 0 to scalar field infinity. They will obey rather hard restrictions. You have to find them. And once you have them, they are predictive. And it is this type of prediction that is a crucial feature of quantum gravity when you associated the ultraviolet completion with an ultraviolet fixed point. And there are pretty general features that I want to convince you, pretty general and pretty interesting features that come out of it. Note, this is a predictive scheme. There's something more than just simply saying we have a few renormalizable couplings that we can choose freely. You get additional constraint from the fact that whole functions have to have a scaling form. And the first result is actually the effective scalar potential is no longer polynomial in the presence of gravity. So we are all used to have polynomial expansions. That's actually not the form of a typical potential in quantum gravity. And that, of course, has immediately a lot of consequences because that fixes now important features, let's say, of the inflaton potential, the Higgs potential for Higgs inflation, how it behaves for large field, or the Cosmon potential for dynamical dark energy or quintessence. So, main lesson in quantum gravity, these potentials are not arbitrary. And the study you have to do is, of course, first you just couple gravity to a scalar field that goes sometimes under the name of dilaton quantum gravity. There's quite some extensive literature on that by now. So let me give the first result, perhaps the most important result. So let's stay a little bit of it. What is it? It is the potential, the effective potential of the scalar field divided by the fourth power of k. So this is a dimensionless quantity. And that will depend on some dimensionless version of the scalar field. Let's say the scalar field is chi, then we take chi squared over k squared as rho tilde, and then x is actually the log of this rho tilde. So what do you observe? Well, you see it is flat on one side, it is flat on the other side, and there is a small change between those two. But essentially it's flat. So that's already what was reflected before by our single quartic coupling. And the fact that it has this simple form is actually not difficult to understand. So the logarithmic change of the potential is proportional to k to the 4. So the scaling solution is that the potential is actually proportional to k to the 4 as well, with some well-known coefficient. And the only change between this part here and the large field part here is that there's a different number of effective massless degrees of freedom for zero scalar field, or let's say for an infinite value of the Higgs field. So that's the general feature, how the effective potential looks like. And I've even simplified it for you. The potential is here just this blue line or this orange line. It's just a constant. Neglect the small changes. It's a constant. So that's pretty simple. Seems boring, but you'll see it's not. There's a second quantity that I have shown here, that is this function W, that has to do with the coefficient of the curvature. So again, very simple. So if you look at functional renormalization, you have, of course, not only the potential as a function of the scalar field, but also the coefficient of the curvature scalar as a function of the scalar field. That's sometimes called variable gravity. And what you find is that, again, this dimensionless ratio, where this f is just divided by k squared in order to make it dimensionless, that this is a constant for chi going to 0. But when the scalar field grows, it actually grows, and it grows exactly proportional to chi squared. It's again very simple, because there is the so-called non-minimal gravity scalar coupling, chi squared times r. This is even perturbatively a renormalizable coupling that's present, and that tells you when the scalar field chi gets large, that this coefficient of the curvature scalar gets large. And when chi goes to 0, then a constant remains. That's all. So that's the picture. That's the general feature, how in quantum gravity the effective potentials look like. They get little riddles, little deformations, and so on, due to non-zero gauge couplings and so on. It's not important. The important thing is just that. You would say, that's pretty boring. What type of cosmology will we get for that? Well, pretty interesting one. Really interesting one, I promise you. Because once you do a Weil scaling, the effective potential in terms of a properly normalized scalar field now looks in this way. So it is a flat tail for phi going to minus infinity, which corresponds to, in the original language, to chi to 0. And it goes exponentially to 0 on the other side. So that you see, okay, that's of course something we really like. That's inflation on one side, and then dynamical dark energy on the other side, with the potential going to 0. That comes out just from these very, very general features. There's a lot of work on quintessential inflation. So what I think is the new point I want to share with you today is that this is actually the potential that comes out from the simplest quantum gravity computation. While scaling, most of you know, just very quickly, you change your metric to a new metric by just a field redefinition. You change your scalar field in order to have your kinetic term essentially constant. So phi is just a log of chi. And then if you do this type of field redefinition, your scalar potential changes. It is the effective potential U that was constant before, multiplied with the fourth power of the Planck mass divided by F squared. You see that is just the square of this rescaling factor. The fact that you have a square root of G in front of the potential, and square root of G just scales in this way. So it's a very simple translation. And now we do it. So we start with this potential. U is some constant times k to the 4. F is another constant times k squared plus this non-minimal coupling, chi squared proportional to chi squared. So that is this drawing here. And then we do the Weyl scaling. Very simple exercise, not complicated. So what you get is you have from the constant term, this goes now this u naught times m to the 4. And then you have this over f squared, and f squared, you remember this was a constant plus chi squared, and chi squared is exponential phi over 2m. So you get really this potential that goes exponentially to 0, and it goes to 0. It does not go to a constant. So we had the constant. If you think about the cosmological constant problem, you have a cosmological constant. Your u times k to the 4, that's the cosmological constant if you wish. That's there. That's actually the scale k is arbitrary. It's the only scale that you have there that sets the scale in your theory. But there is no other small parameter. And you get out immediately this form where for phi to infinity, the potential goes to 0. And you just have now a cosmology where you run down from one side to the other. So you start with chi equals to 0. You end in the infinite future with chi to infinity. And you start from something like inflation and end with something like dark energy, and you solve the cosmological constant problem because in the infinite future phi is infinite, and then the potential is really 0 and not a constant. So quantum fluctuations are already taken into account. They give this constant u, but once they are taken account, you do the Weyl scaling and it goes to 0. So that's an important observation. And that is, if you think about mass scales, what happens after Weyl scaling? After Weyl scaling, you see the scale k, that was our only scale before, has completely disappeared. It's no longer present in the Weyl scaled form. Now you have a new scale, the Planck mass. But the Planck mass has been introduced only by the field redefinition. We did not change the theory. We just express the same theory with different fields, which is in quantum field theory, of course, a standard thing to do. So the Planck mass only comes in there, but it's not a parameter. And that explains why we never have to introduce small parameters in your theory. Our u and w, the coefficients are of order 1. The only scale is k. It's the only scale if you have no intrinsic masses. This is characteristic thing for any scaling solution. So that's it, and you rescale it, and you get a solution of the cosmological constant problem. Really, there's nothing to change. There's no tiny parameter that has been introduced. The cosmological constant goes to 0 in the infinite future, and it's today very small because the universe is very old. And this ratio chi squared over k squared has grown in the course of cosmology to very large values. And you actually can construct rather realistic models based on this idea. Javier Rubio has done that with me at some moment. with inflation, kination, freezing, tracking, acceleration. This is not my topic today. It just tells you that this is not only very rough thinking, but in principle, once you have this potential and once you can compute it, you can really make predictions. Actually, the simplest models sometimes don't work. Unfortunately, Higgs inflation did not work, but some other models can work. I want to make a few comments on quantum scale symmetry and then on the beginning of the universe. Quantum scale symmetry, that means a situation where no scale is present in the effective action, even not the scale k. So that is realized when you go with k to 0 or when you go with k to infinity. Then you have two fixed points, not only a scaling solution, but two fixed points with unbroken quantum scale symmetry, with exact quantum scale symmetry that is unbroken when chi goes to 0, and that is spontaneously broken when chi goes to infinity. And now, since when chi goes to infinity, any non-zero value of chi breaks scale symmetry spontaneously, then you will get a Goldstone boson. Well, these simple properties of quantum scale symmetry, they are directly visible in cosmology. Because if you go close to the ultraviolet fixed point, then you are close to a situation, you are close to the situation of exact scale symmetry, with only the fact that chi is not yet exactly 0, you are violating it. And this gives you a primordial fluctuation spectrum that is almost scale invariant. So that's the simple explanation for the almost scale invariant primordial fluctuation spectrum. And notice there is no tuning of parameters. Normally, if you construct inflationary models that should get a flat spectrum, you have to tune your parameters. You have really to be careful not to produce nonsense and so on. Here it just comes out as a very generic feature. And the other generic feature is related to dynamical dark energy. Because if in the infinite future you have again exact scale symmetry, then in the infinite future you will have an exactly massless Goldstone boson. Spontaneously broken continuous symmetries give you Goldstone bosons. Now we are pretty close to the future on Planck scales, because the universe is pretty old in Planck units, but we are not yet there. And that is why we get a very light scalar field, and the scalar field has actually a mass which is of the order of the present Hubble parameter. So sometimes people say quantum fluctuations make that very unnatural. It's the contrast that is true. Quantum fluctuation produce you the infrared fixed point, and due to the exact quantum scale symmetry at the infrared fixed point, you produce a very natural reason for getting an almost massless Goldstone boson, and that's of course my cosmon of dynamical dark energy.
Christof, it's half an hour.
Okay. For some reason, I cannot move my screen anymore here. So I think I will do in 5 minutes. Dynamical dark energy, that comes out now in a very natural way. We have seen our important relation is the potential divided by f squared if the potential is constant and f increases proportional to chi squared, then this goes like 1 to the chi to the 4. So that goes to 0, and that you see this ratio is actually the same in all metric frames. And you see always this effective cosmological constant will really go to 0. And actually in the late universe, the effective action is very simple. It's just chi squared times the curvature scalar plus a constant, and that's it. That's the effective action for the scalar field coupled to gravity. And then if you do Weyl scaling, this gives you really this vanishing cosmological constant. And that was actually the setting of my original prediction of quintessence, which was a real prediction. At the moment, I could not compute it, but the basic mechanism was, of course, exactly this what I had in mind when I predicted this asymptotically vanishing cosmological constant that should lead to dark energy, to homogeneous dark energy. And I think it's still a very nice prediction, even though for being compatible with observation, you need a few more things that I will not discuss today. So the overall picture of the universe is very simple. We start in the infinite past from the ultraviolet fixed point. Its vicinity is described by inflation. You end in the infinite future by the infrared fixed point, and we make here a crossover, which makes the dominance of quintessence in the present period. These models are very simple. They include very early dark energy for inflation. They include early dark energy, often in the form of scaling solutions, and they can include a present dark energy dominated epoch. A last few remarks on metric frames. If we do a while scaling, we map actually this variable gravity model universe is fixed to a mass to a universe with fixed masses and a standard expansion history, or vice versa. One should not forget that while scaling is not a form of coordinate transformation. It does not leave the geometry unchanged. And that is an important thing that is very often forgotten when people discuss about singularities and things like that. Because if you do a while scaling from the standard inflation picture back to this picture in which I have done the quantum computations, you find that the universe actually lives eternally. It lives since ever. It started with a universe at the beginning of the universe, which was simply boring. It was empty, only expectation values of the metric and the scalar field, and then fluctuations, as in every quantum field theory, so correlation functions different from zero. So that was the beginning, just fluctuations, nothing else. And then out of that, all the rich variety have grown, because this type of universe has an instability towards the increase of the scalar field and also towards the increase of the metric fluctuations. So you can now compute, the picture looks different. It's not 13.7 billion years old. The universe is infinitely old. The fluctuations that we have observed, they have been observed about 5,000 billion years ago. All that is in physical time, which I can discuss, but I will not do it. But in the beginning, you have really this story. The universe was like light, like emptiness, not much there. Out of that, everything has grown. And this is precisely equivalent to the Big Bang story, where you had this very dramatic explosion of inflation around 10 to the power minus 40 seconds, you get a singularity. But recall, field relativity maps from one to the other by a field transformation. And this field transformation gets precisely singular when chi goes to zero. And this singularity of the field transformation, that transforms the very regular solution I have to the Big Bang solution, which seems very singular. When the singularity is nothing else than a so-called field singularity. You know coordinate singularities, where your Antarctica appears in certain coordinate systems as a singularity. Well, you have to go further. Once you have field transformations and not only coordinate transformations, you can create singularities by an unsuitable field coordinate system. And that is, in this case, the Einstein frame, because the Einstein frame obscures the simple scale invariance when chi goes to zero. I think with that, I stop. My conclusions are that fluctuations of the metric really matter. They are important. They have a strong influence on the behavior of scalar potentials at all field values. Quantum gravity is indeed relevant for early cosmology, but also for late cosmology, because we got this dynamical dark energy. That's late cosmology. That is again dictated by these simple scaling solutions for that are necessary for an ultraviolet fixed point. So I think quantum scale symmetry is actually a central ingredient for our understanding of cosmology, and predictions, I think, will come more and more. Some of them we may like, some of them we may not like, and we may be able to discard certain models and select certain models in the future. You're still at the beginning stage, but I'm personally confident that one can really do computations in quantum gravity, really do computations what the quantum fluctuations do. Thank you.
Okay, thank you very much. Any questions? Gia has a question.
Can you hear me? Yeah.
Yes, that's good.
So Christof, I have the following question about this approach that you gave about quantum gravity, because in Einstein gravity we have black holes, and this is a pretty powerful part of information, because we know that because we have black holes in transplanckian collisions, we never reach momentum transfer comparable to the Planck mass or higher, because everything is dominated by black hole formation. And so in other words, if you collide the plus and minus with the center of mass energy.
Let me answer to that in a very simple way. You see, what I do is I have a scale K for which I include fluctuations or do not fluctuations. There's a several wait, let me answer. The issue is what is the momentum dependent.
Christof, I think he has to complete the question.
Okay, I didn't ask the question. So my question was, so in other words, we know that the collisions transplanckian collisions are always soft because the momentum transfer is much lower than the Planck mass. So in other words, what Einstein gravity is telling us is that we never probe momentum transfer above the Planck mass, and therefore so what is the story with asymptotic safety? What does it even mean?
Okay,
if you can never probe a momentum transfer above the Planck mass, what do you call asymptotic safety?
So first of all, there's a difference between momentum transfer and a physical process and the momentum of fluctuations. So fluctuations, there is no reason why you should not include fluctuations to arbitrarily high momenta. They are just there in your functional integral. You start formulating your functional integral and there are all fluctuations in it. You cannot avoid that.
No, but that is not probing.
All right, now it's my turn. Now, a different issue is how the quantum effective action looks like, because that will decide on scattering states and so on and so forth. So you have to compute the momentum dependence of the quantum effective action after your fluctuations are all included. That's the issue. So I'm not sure actually what happens to black holes. If black holes really remain singular or not, that is an issue about the precise form of the quantum effective actions of their momentum dependence at high momenta. It is actually possible that not all momenta can be reached for this black hole scattering. Fine, that's a question of how the solutions look of a given quantum effective action. But nevertheless, whatever it is, you have to include fluctuations of all momenta in your functional integral. There is no choice. There is nothing where you can say, I have an infrared, ultraviolet cutoff or something like that. That has to come out if it's there.
Yeah, but there is a difference between the momentum and the momentum transfer. Momentum per se doesn't probe any short.
But it's the same for momentum transfer.
Because you can, look, let me give you an example. Take a particle that you boost with a very soft potential for an arbitrarily long time, that particle in your reference frame can have an arbitrarily high momentum, but you are not probing Planckian physics with that.
Oh, what's your point, Gia? What's your point? Are you saying we have not to include fluctuations with arbitrary short distances and arbitrary high momenta? I mean, once you formulate quantum gravity as a functional integral, all fluctuations are there, period. And then you read out at the end what the physics is.
But sure, but what I'm saying is that that's precisely what I'm trying to understand. That's my question. That's you understand, you are the one that is giving me a theory of quantum gravity, so it's your responsibility to answer this, not mine. I'm telling you, what's the meaning of momenta in your description, much larger than Planckian? How should I understand them? As simply some momenta that are boosted, or which do not probe any trans-Planckian physics, or as momenta that are physical and they have to do with momentum transfer. But that's your responsibility, not mine.
Well, I give you a very simple answer. I just classify I just classify fluctuations according to Fourier, let's say, to Fourier decomposition. You can take another decomposition on the sphere, and you just have to include all of them. And that's it. And then you find out at the end what your effective action is. I mean, what should be wrong with that simple procedure? That's what we always do in quantum field theory.
But that's the only part. Why? What I'm trying to understand, you seem to present an argument that you have a consistent theory of quantum gravity.
Yes, I do.
I don't see why just simply in spectral representation, including all the momenta and dealing somehow with them, is a fully fledged theory of quantum gravity. I don't understand
well,
that.
It depends. It depends on the outcome. Maybe the outcome is not unitary. Maybe the outcome has other flaws. Then I would not claim it's a fully fledged theory of quantum gravity. But the procedure of formulating a quantum functional integral is certainly a consistent one. There is no problem. You can even take care of the gauge symmetries in a proper way. And then you have to look what comes out. And if the outcome is reasonable, then it's a consistent theory of quantum gravity. If it's not reasonable, then you better look to go to a different functional integral. But I think, the basic approach of saying I formulate my theory as a functional integral, that's a very reasonable one. That's actually how we define all sorts of non-perturbative quantum field theories. And there's no reason why we should not do it for the metric fluctuations or the Vierbein fluctuations or even other pre-geometry formulations of quantum gravity.
Okay, I don't want to take too much time, so we can continue.
I think in view of the time, let's take a break. You're welcome to continue discussing through the break. And unless there are any other very quick questions, let's thank Christof again for a very interesting talk. And I think we should come back at 4:35 Central European time, if that's okay. We've got 2 more talks. And they'll be at 4:35 and at 5:15.
I think 4:30.
Yeah.
So we just assign ourselves to the rooms, or how does it work? We just click on.
Yes. So in principle, I guess according to the order of the talks, maybe the first speaker of the to the first room, second to the second. So I can do this if you want. I can move you to the specific rooms.
Oh, Gia, if you want, we can just continue the discussion now.
Okay, whatever. Yeah, I mean,
or we just leave rooms open, and then whoever wants to move there. Yeah. So Arthur, I see he is in the room 1. So if Valerie is here.
So, Gia, that's, I mean, what is your basic point? You do not want to include fluctuations with arbitrary momenta in your functional integral, or what are you proposing not to do?
No, that no. Of course, we